Welcome to the Deep Dive, where we slice through complex topics to bring you those crucial insights. Today, we're plunging into a foundational piece of your network, something happening constantly behind the scenes that most people never even think about. ARP, the Address Resolution Protocol. Our mission is to illuminate this often overlooked hero, giving you a true shortcut to being well informed about the very plumbing of your local network connections.
It's true. ARP is definitely an unsung hero, a silent orchestrator, really, that enables fundamental communication right there on your local network. What's truly unique about it is how it acts as this critical translator, kind of bridging the logical world of IP addresses with the physical world of hardware addresses. It sits at a fascinating intersection, making it a truly vital piece of the networking puzzle. We'll break down its inner workings, explore its different variations, and yeah, even uncover how it can be exploited by those with, well, malicious intent.
Right. So get ready for some genuine aha moments, maybe some surprising facts, and practical insights that will deepen your understanding of how your devices actually talk to each other. Okay, let's unpack this then. For anyone connecting to a network, the first hurdle is always, how does my computer actually find another computer or a router on the same network? What exactly is ARP and, what problems it solve?
Okay. At its core, ARP, Address Resolution Protocol, it's the mechanism your devices use to find the physical hardware address that's the MA address of another device, but only on the same local network, and crucially, when all it knows is that device's IP address. Think of it like this. Your computer knows the street address, the IP, of the house it wants to send a letter to, but it needs the specific mailbox number, the ASCII address, to actually drop the letter in. ARP provides that translation. It links the logical layer 3 IP address to the physical layer 2 MSE address.
Oh, okay. So it's the network's essential directory service, but just for local connections. How does that actual lookup process work, like step by step?
It's surprisingly simple, yet effective. First, the host needing to communicate, knowing only the target's IP address, sends out an ARP request. This request is a broadcast message. It's essentially shouting to everyone on the local segment, hey, who has IP 192.168.1RA0? Tell me your ME address.
Okay, a broadcast. Got it.
Second, the specific device that actually owns that IP address, it receives the broadcast and sends back a direct ARP reply. That reply contains its unique ARP reply.
Directly back to the requester.
Exactly, not a broadcast. And finally, the requesting host stores this newly learned IP to MAC mapping in its temporary ARP cache. That way, it doesn't have to ask again immediately for the same destination.
Right, avoid shouting every single time. And this brings us to that interesting classification you hinted at. ARP is often called a Layer 2.5 protocol. We've talked about it bridging layers, but why is that 2.5 designation so significant? What makes it sit in that unique middle ground?
Yeah, that layer 2.5 thing. It isn't just a technical quirk. It really highlights ARP's unique and absolutely critical role. It's like the network's unsung diplomat. See, layer 3 devices, like your computer's operating system, they think in IPs, right? Logical addresses. But layer 2 devices, like network switches, they operate purely on mass addresses, physical hardware identifiers burned into the network card.
Different languages, basically.
Totally different languages. ARP is the essential interpreter that translates between these two. Without this precise translation, your high-level applications, your browser, your email client, they literally have no way of finding the right physical wire, the right network interface card to send data to on the local network. It's the grease in the gears that makes IP routing even possible across local segments.
Okay, that deeper explanation really helps solidify the why. It's not just bridging, it's enabling. And you mentioned the ARP cache earlier. So this temporary table in memory, the ARP cache, that's essentially the brain of ARP. What exactly is stored there and how does it make communication more efficient?
Exactly. The ARP cache is that temporary table living in your device's memory. It holds those freshly learned IP to MAC address mappings. Its importance really can't be overstated. By storing these mappings, your device avoids sending those ARP requests over and over again. Every single time it needs to talk to a known IP on the local network.
Right.
Imagine having to ask for someone's address every single time you wanted to talk to them. It'd be incredibly inefficient.
Yeah, annoying too.
The cache drastically reduces network traffic, that broadcast chatter, and speeds up communication.
So it's like the network's short-term memory. Makes sense.
Yeah.
And just like our short-term memory, entries don't stay there forever, do they? There's an expiration date, a timeout.
Exactly right. These entries have a default timeout period. And this varies quite a bit depending on the operating system. On Windows, it's typically around maybe 2 minutes. On Linux, it's often dynamic, could be around 60 seconds, and entries will expire if they're not used.
So they age out.
They age out. This timeout concept is a critical trade-off for network designers. A shorter timeout means your device sends more frequent ARP requests, which means more network traffic, but it also reduces the risk of using a stale, outdated ASCII address if a device, say, changes its network card or moves.
Okay.
A longer timeout saves traffic, but you increase the chance of attempting to use an outdated mapping, which would fail.
So it's a constant balancing act.
It really is.
That balancing act is fascinating. Okay, let's get a little more technical for a second. Peel back another layer. What does an actual ARP packet look like on the wire? What are the key fields inside?
Certainly. An ARP packet isn't super complex, but each field serves a crucial purpose. Key fields include things like hardware type, like Ethernet protocol type, usually IPv4 hardware size, protocol size, and crucially, the opcode. This tells us if it's a request, which is opcode 1, or if it's a reply, opcode 2.
Request or reply. Simple enough.
And then, of course, you have the sender MAC and sender IP addresses and the target MAC and target IP addresses. These fields collectively allow devices to figure out who's sending the request, who it's for, and what information is being exchanged, usually what's your MAC. Now, beyond the basic request and reply, ARP has a few, let's say, specialized forms. One that often surprises people is gratuitous ARP.
Gratuitous, like unasked for.
Exactly. It's an unsolicited ARP reply sent by a host without being asked. It's like a device just volunteering its contact info to the network.
Why would it do that?
Well, for crucial purposes, like detecting IP conflicts. If a device boots up and announces its IP with a gratuitous ARP and another device on the network already has that IP, that second device might send back a reply saying, hey, that's my IP, flagging a conflict. It's also vital in failover scenarios. Think about redundancy protocols like HSRP or VRRP, where you have backup routers or firewalls. When the backup device takes over, it sends out a gratuitous ARP immediately. This tells all the switches on the network, hey, the MME address for this important IP address has changed. Send traffic to me now. It ensures a really seamless traffic flow transition.
So it's almost like a self-healing or self-announcing mechanism. Pretty cool. Then there's proxy ARP. How does a router get involved in responding for other devices? That sounds a bit odd.
It is a bit odd, yeah. Proxy ARP is where a router intercepts an ARP request meant for a device on a different subnet, but one that's reachable through that router. The router basically lies and says, yep, that IP address, send packets for it to my MAC address.
It pretends to be the other device.
Kind of. It tricks devices on one subnet into thinking they're directly communicating with devices on another, even though they're separated by the router. It's a bit of a workaround. You don't see it everywhere, but it can be used in specific network designs to make things work without complex routing setups on the end devices.
Okay. Less common, but good to know.
And then there's inverse ARP, or an ARP. This operates in reverse compared to standard ARP. It maps a known layer 2 address, like a frame relay DLCI or an ATM VPI VCI, to an unknown layer 3 address, the IP.
So MC to IP, kind of like RRP.
Similar goal to RRP, yes, but used in different contexts. You wouldn't typically see in RRP on your standard Ethernet network today. It was more for specific older wide area network technologies like frame relay or ATM.
Gotcha. Okay. Historical context. Now, here's where it gets really interesting and, frankly, a bit unsettling for network security. Yeah. Let's talk about the dark side of ARP, ARP poisoning or spoofing.
Yes. ARP poisoning is a, unfortunately, common and dangerous network attack. A malicious actor on the local network sends out fake, crafted ARP replies. The goal is to trick other devices on the network, maybe your computer, maybe the default gateway router, maybe even the switches themselves, into incorrectly associating the attacker's MC address with the IP address of a legitimate device.
So they impersonate someone else.
Exactly. Imagine all your internet traffic, your banking logins, your emails, sensitive work data suddenly, silently flowing through an attacker's computer instead of directly to the router.
Wow.
That's the classic man-in-the-middle or mid-M attack via ARP poisoning. They can eavesdrop on everything, potentially modify data as it passes through, or just block your connection entirely.
It's a silent hijacking of your traffic.
Pretty much sums it up. It's a fundamental vulnerability because ARP itself was designed way back when networks were generally more trusted environments. It doesn't have built-in authentication.
That sounds like something that could be absolutely devastating. So what are the crucial mitigation strategies? How do we defend against this silent hijacking?
Thankfully, there are several critical defenses network administrators can deploy. Enabling dynamic ARP inspection, or DAI, on network switches is probably the primary one.
Yeah, what does that do?
DAI is essentially the switch acting as a gatekeeper. It cross-references incoming ARP packets, both requests and replies, against a trusted database. This database usually maps switch ports to authorized IPM spaintings, often built using DHCP snooping. If an ARP packet comes in that doesn't match the trusted bindings, the switch just drops it.
Okay, so it verifies the ARP messages.
Precisely. For really critical devices like servers or the default gateway, you can also use static ARP entries. You manually configure the correct IP to MAC mapping on devices or switches. This static entry usually can't be overwritten by a dynamic, potentially malicious ARP reply.
Hard coding the right address.
Right. Additionally, things like employing port security on switches, which can limit the number of MAC addresses allowed to communicate on a single switch port, can help. And maybe even using MAC address filtering, although that can be harder to manage. These measures combined make ARP poisoning much, much harder to pull off.
So layers of defense are key.
Absolutely. It's not just good practice, it's really critical for maintaining network integrity these days.
It truly highlights how crucial it is to understand these, seemingly small protocols. Their vulnerabilities can have massive implications. And speaking of ARP's place in the network world, let's talk about its relatives and how it fits into the broader landscape. We differentiated inverse ARP briefly, but how does ARP specifically differ from RARP, reverse ARP? You mentioned a similar goal earlier.
Yeah, the names give it away. ARP resolves an IP address to an API address. You know the IP, you need the MS. ARP, reverse ARP, does the exact opposite. It resolves a NAC address to an IP address. You know the physical address, but you need to figure out its assigned logical IP.
Why would you need that?
Historically, it was used by diskless workstations or simple devices when they booted up. They knew their own MAC address, but needed to ask a RARP server on the network, hey, what IP address should I use? But RARP is largely obsolete today. Modern networks use much more robust and feature-rich protocols like BOOTP and especially DHCP for automatic IP address assignment.
Okay, so RARP is mostly a history lesson now.
Pretty much, yeah. DHCP is king for that job.
All right, here's a critical question that often trips people up, I think. Can ARP work across routers? Does that layer 2.5 magic extend beyond a single local network segment? The answer is an emphatic no. Absolutely not. ARP is strictly a layer 2 protocol, meaning it only functions within a single local subnet, a single broadcast domain.
Right. Routers are layer 3 devices. Their job is to forward packets between different subnets based on IP addresses, not MAC addresses. Each router interface essentially acts as an endpoint for an ARP domain on that specific network segment.
So if my computer wants to talk to a server on a completely different network,
your computer will use ARP to find the MAC address of its default gateway, which is the local writer. It sends the packet to the router's MC address. Then the router takes over. It looks at the destination IP address, consults its routing table, and figures out the next router or network segment to send the packet to. Then the router will use ARP on its local segment to find the MC address of the next hop device. ARP stops at the router boundary.
Okay, crystal clear? Local only.
This raises another important question, especially given the shift in networking. Is ARP used in IPv6?
Ah, good question. Does the new version of IP still use it?
No, it doesn't. ARP is specifically for IPv4. IPv6 completely replaces ARP with its own more comprehensive mechanism called Neighbor Discovery Protocol, or NDP.
NDP.
Yep, Neighbor Discovery Protocol. NDP handles a much broader range of functions than just address resolution. It does the equivalent of ARP finding the MA address for an IPv6 address, but it also handles things like duplicate address detection, DAD, finding routers on the network, tracking neighbor reachability. It essentially consolidates the functions of ARP, ICMP router discovery, and ICMP redirect from the IPv4 world into one unified protocol suite.
So IPv6 learned some lessons and bundled things together.
You could say that, yeah. It's designed to be more efficient and integrated.
Okay, so back to IPv4 and ARP. If a host sends out an ARP request but simply doesn't get a reply back, what happens then? Does the communication just fail immediately?
No, it won't give up immediately. A well-behaved network stack will typically retry the ARP request several times, maybe with a short delay between retries.
Trying again just in case the first one got lost.
Exactly. Or maybe the target device was just a bit slow responding. But if it still doesn't get an ARP reply after those retries, then yes, the communication ultimately fails. The sending host simply doesn't know the destination MAC address needed to actually send the data frame on the local network. You'll often see an error message pop up, something like destination host unreachable or a similar network error.
Right, that familiar error message.
It's also useful, I think, to quickly clarify the difference between dynamic and static ARP entries we touched on.
Good idea.
So dynamic ARP entries are the ones we've mostly been discussing. They're learned automatically through that request reply process we walked through. And critically, they expire after that configured timeout period. They're temporary.
Learned and forgotten.
Precisely. Static ARP entries, on the other hand, are manually configured by a network administrator directly on a device. You literally type in the command saying, this IP address always maps to this specific MAC address. These entries are persistent, they don't time out, they stay in the cache until the device reboots or until an administrator manually removes the entry.
And why use static? We mentioned security.
Security is a big reason, especially for critical infrastructure like routers, firewalls, or important servers. It prevents ARP poisoning for those specific entries. It can also sometimes be used to guarantee specific traffic paths, although that's less common. But mostly it's for security and stability for key devices.
Makes sense. Lock down the important stuff. So let's bring this all back home. What does this all mean for you, the listener, in the real world? Where do you actually see ARP? Or rather, where is ARP working for you every single day without you realizing it? Think about it. Every time your PC connects to the internet, the very first thing it needs to do is talk to your home router, your default gateway. It needs that router's MAC address. That's ARP at work right there.
Absolutely.
Network switches, the boxes connecting all the wired devices in an office or home. They rely heavily on those IP to MAC mappings learned via ARP snooping or stored in their own tables to forward traffic efficiently. They need to know which physical port leads to which MAC address to avoid flooding traffic everywhere.
Yeah, switches build their MAC address tables partly based on AR key traffic they see.
Routers, as we discussed, use ARP constantly to resolve the MAC address of the next hop device on their directly connected local segments when they're forwarding your packets across the internet.
Every hop potentially involves an ARP lookup.
And those high availability systems we mentioned earlier, load balancers distributing traffic across servers, firewalls working in pairs, failover clusters, they actively use gratuitous ARP, sending out those unsolicited updates to ensure seamless transitions when services shift from one physical box to another, ensuring minimal downtime for you.
It's truly fundamental. It's happening constantly, underpinning almost all local IP communication. And if you're curious, if you actually want to see this in action, you can easily peek inside your own device's ARP cache.
How do you do that?
Well, on Windows, you can open up a command prompt and just type ARP-A. That'll show you the current entries, the IPs, and their corresponding MA addresses. If you wanted to clear it, you could use ARP-8D, though usually there's no need unless you're troubleshooting.
Okay, ARP on Windows. What about Linux or macOS?
On Linux or macOS, the more modern command is usually ipnay for neighbor, or the older RPN often still works too. To clear the cache on Linux, it's something like ipssnay flush all.
Ipnay, got it.
And for troubleshooting, especially if you suspect something weird might be happening, like maybe spoofing, on Linux there's a handy tool called ARPing. You could do ARPing-C3 followed by an IP address to send ARP requests directly to that IP and see if you get replies, maybe even unexpected ones.
Useful. And Wireshark, I assume.
Oh, absolutely. Wireshark is fantastic for this. Just apply the display filter ARP and you'll see all the ARP requests and replies flying across your network segment in real time. It's quite illuminating.
We've definitely covered a lot of ground today. We've hopefully transformed what might seem like a small, obscure technical detail, ARP, into something you can see as a foundational element of how our digital world communicates locally. The address resolution protocol, it's critical to every single local connection you make. It has surprising versatility, as we saw with things like gratuitous ARP and proxy ARP, and understanding its security implications, particularly ARP poisoning, is just absolutely vital for anyone interacting with networks today.
Absolutely. And if we connect this to the bigger picture, ARP is really a perfect example of those intricate, often invisible layers that make modern networking possible. It's constantly translating, constantly adapting behind the scenes so our devices can simply talk to each other. Whether it's your phone streaming this deep dive right now or your computer accessing a website, it's that behind-the-scenes magic that makes the internet and local networking feel so seamless and effortless most of the time.
So the next time you connect to a Wi-Fi network or stream a video or send an email, maybe just take a moment to reflect on this hidden hero of the network, ARP. And perhaps consider this. How many other invisible translations and protocols are constantly working, constantly chattering away just for you to experience the digital world? Understanding these fundamental building blocks like ARP truly empowers you to comprehend the complex, amazing digital world around us. And that, I think, is a deep dive worth taking.